No, I know. No, it's not like that. It's like you don't like it, then you ask for the change. But if
Hello? Yeah. Okay, so our last speaker today is Yelena Guryanova from Vienna. And she'll tell us about being realistic when I talk about quantum thermodynamics.
Great. So in this lecture, first of all, thank you all for coming and thank you for those who are listening online. In this lecture, I would like to address something that has been glossed over in the last couple of lectures. And it's this idea about having an idealization in physics. So idealizations, like for example, idealize a gas and derive some equations about it, are useful for simplifying models and for making problems tractable and calculable, and for gaining some intuition, perhaps, as to why certain phenomena occur. And in physics, we have often this desire for simplicity, which I guess comes back to this reductionist view that the more simple something is, the more beautiful it is, which arguably goes back to some kind of ancient Greek philosophy. But here I'd like to argue that sometimes this leads to a tension. And I'd like to quote Armin, actually, over there, who wrote a paper recently about where he tried to derive Bell inequality, so a type of experimental test, using the Platonic solids. And he was like, oh, so beautiful, the Platonic solids. And in the beginning, in the introduction, what they find is that using these beautiful Platonic solids, so they use them with the directions of the measurements. To quote him, he says, this leads, so they depart from mathematical beauty and then focus on doing something more experimentally friendly when they conclude that this leads to a more sort of Bell equality that is remarkably inelegant. And we conclude with a discussion of the danger for theoretical physics to become and remain too focused on mathematical beauty at the expense of developing connections with experiments. So, and now we go on to a part for Nuria. Nuria loves paradoxes. I'm going to start with a paradox. So we're going to have two sides of the course. On the left-hand side, we'll start with quantum measurements. So quantum measurements. On the right will be quantum thermodynamics. Quantum measurements. This is from the postulates of quantum mechanics. We know that they're described by POVMs, right? Described POVMs. So some set I, MI, and these things are normalized, of course. Right? We're all used to seeing this. The second thing we know about measurements is, well, we have a state after the measurements. We have like an update rule in quantum mechanics. That's in R. And the update rule is that, so this will be, my tilde is always going to be the post-measurement state, right? So the post-measurement state, Ri, on getting outcome I from my POVM, is this thing, and I normalize it, right, by the probability of getting it. The trace of this thing. And I. This is the outcome I. And well, finally, the probability, we have some notion of probability, and it's given by, of course, the Born rule. And it's the denominator in this expression. So Pi for outcome I is the trace of Ni for Okay, what do we know about quantum thermo? We're in quantum thermodynamics. We have a notion of reversible global time evolution. Notion of global reversible This N is like a shun, the English ION. I can't remember. So, the state at a later time t is gotten by evolving the initial states where it's 0. We have this notion of the emergence of thermal states, and I can give you some reference for this in the notes later. The emergence of thermal states through thermal states through entanglement and coarse graining. And lastly, and rather importantly, we know that the unitary orbit of thermal states is full rank. So what's the unitary orbit? It's the set of states sigma, where sigma is u, let's call it tau beta, of course, beta u dagger. So the unitary orbit of thermal states is full. Thermal state is of course full rank, and so any unitary I can use to rotate it results in some other state sigma, which is necessarily also full rank. Now, this has been shown to imply the third law of thermodynamics. And there are many ways of stating the third law of thermodynamics. I like to think of it as an unattainability principle. So you cannot call a state to absolute 0. State to a ground state, 0, which in non-degenerate cases is a pure state. So we cannot call something to the pure state. And Ralph very helpfully had this whole board of red at the end of his lecture, where he showed that calling something to 0 necessarily has divergent resources. So it's impossible to call a quantum system to the ground state with finite resources and finite time or finite complexity. So now we arrive at this paradox. So I can think about, on the left-hand side, we have quantum measurement. So let's imagine we measure a thermal state tau. What happens when I do a measurement? Well, I have a measurement apparatus, I couple it to my system, I do some interaction, and let's say I want to measure the energy, the energy eigenbasis, I get the outcome, outcome I, corresponding to, with probability, measured, I want to put in the energy eigenbasis. And the probability is the Gibbs. And I get a state, right? I get the state corresponding to my measurement results, EI. Okay, does anyone see where this is going? On this side, I'm going to imagine cooling. The same one with a copy of a thermal state using quantum thermodynamics paradigm. So, for example, you can have a fridge coupled to a target system, like a laser, or you could do bulk refrigeration. But you always have to invest work to cool something, right? And invest in work. And how much we can cool is limited by the third law of thermodynamics. So we can't actually ever get here. So here's the problem. So on the left, after I do a measurement, trivially measure it, I arrive at this state, EI, which is a pure state. And on the right-hand side, in the thermodynamics paradigm, I'm told I can never get a pure state, because I have to obey the laws of thermodynamics, right? So here I'm not allowed pure states. So we arrive, this is supposed to be set up. So we arrive at a contradiction. How can it be that the laws of quantum mechanics leave you in a state that is forbidden by the laws of thermodynamics? Good. So in reality, then, we know that measurements are performed in labs. People do experiments, we can experimentally verify things, and we know that in reality, the post-measurement state of a system is never truly pure because errors occur. We have photon count, dark counts, mistakes in our, well, not saying mistakes, let's say hardware problems, things like this. But what it actually boils down to is a fundamental limitation of quantum mechanics to ever get a pure state. So it's not technology that's limiting us, it's a fundamental property of quantum mechanics. And what we'll see is that pure states can be very well approximated with high power consumption equipment, right? So the more energy I pump in, the closer I get to a pure state. So in reality, in a lab, like the lab is on all the time. It's wasting huge amounts of energy, well, investing huge amounts of energy to get a readout of a hyperfine quantum transition, which is orders of magnitude smaller than the work you're putting in order to make that measurement in the first place. So to understand a little bit more then what a measurement is, let's define an ideal measurement. Ideal. So an ideal measurement is, at a very basic level, an interaction between a system and a pointer, initially uncovered, that correlates them, right? I want to learn something about the system. Rho S will be the system, and rho P will be pointer, and they are taken by some interaction to some final state, rho SP. And okay, let's draw a figure of this. Draw the system like this. And some pointer here and a system here. So initially they're uncorrelated. I interact them and I end up in some final states. Rho tilde, system pointer, such that when I look at the pointer, and this is the point that I stop. So, okay, you have to forget collapse and forget anything associated with this. This is what I call a measurement, right? This interaction here. And the properties that this final state will have will define what an ideal measurement is. So I'm not going to tell you what it means to look at the pointer and observe an outcome. I don't know what that is, but I can definitely describe you this and this. So when we talk about seeing the pointer, it's at the level of probabilities. So what I want to do is, this is the interaction such that when I look at the pointer, here's the pointer, I correctly infer, and correctly means with probability 1, the underlying property of the system. So we're going to use energy mainly for this talk. It can be any observable you want. So this means you need to establish a correspondence between the system and a pointer. So let's imagine, for argument's sake, the system is a qubit. And for the states 0 and 1 of the qubits, I need to define some appropriate, let's call them projectors of the pointer. Okay. And in principle, this projector, I'm assuming the pointer is large. I don't need to at this stage, but later we'll see that it has to be quite big. This pointer could be composed of many microstates, right? Many states, psi, probably n here. Yeah. So for example, imagine a hard drive in a computer, the old kind that were made of magnets. So some spins are pointing up, some spins are pointing down, and you can think of this as a collective measurement, right? So if most of them are pointing down, okay, I'll infer the underlying system states of the system to be down as well. So somehow what you do is you split your pointer, you split the Hilbert space, and then maybe this, they have many microstates in them, and so on and so forth. So let's do a very trivial example. Let's imagine that I have some system, some pointer, and they end up in the state 0, 0, system pointer. Now, this is clearly pure. It's perfectly correlated because clearly when I look in this pointer and I see 0, I know for sure that the system is in state 0. It can't be anything else. And the other thing we see, it's classical, right? So this idea of correlating a system and a pointer, we're not looking to have quantum correlations between them, right? It's enough to be classically correlated. In fact, that's all you need to infer the correct state of the system. And indeed, you know, exactly the same with this state here. When I see 1 on the pointer, I know for sure that the system is in state 1.
Yeah, you should go further than the thing outside.
Very hot. It's very warm.
It is. It's also very loud.
In this case also, there's no ambiguity when I get state 1. An ambiguity would occur if I had this state, for example, if I had this component of the state, right? Just for argument's sake to illustrate what I mean. If I look at the pointer and I get the outcome 1, and I think, aha, the system is in the state 1, that's wrong because the system is in the state 0, in fact. This is anti-correlated, right? So here I make an error. In this state, I make no error about the inference of the underlying state of the system, and it's perfectly correlated.
Do you mean this state itself has that kind of term? Like
this state has none of those terms. So here, without any ambiguity, if I get 1 on the pointer, I know for sure the system is in state 1. Yeah. But yeah, we'll get to the ambiguities in a second. So then, following some sort of reasoning, we can argue that there's an ideal post measurement state. So that's this row template, SP up there. And the ideal state looks something like this. Matteo used notation like this in his lecture, and mine has nothing to do with his, so I apologize for that. So what does this mean? So this I'm missing a term. The sum over I, row I. Right, so this row I is just components of the system. These states are pointer states, and there are some off-diagonal terms. So pictorially, it looks something like this. 0. Is this very small? Or 1, 0, 0, and so on. So these are numbers. This is some matrix. So this matrix has come from components, constituent components of the pointer. And I'll explain so clearly something of this form, which is this is back to the example. Is of this form because it's a half 0, 0 10 to 0, 0 plus a half. This is the row 1, 1. 1, 1, 10 to 1, 1. Oops. Right? So 1, 0, 0, 1. So the blocks are essentially one-dimensional in this case on the pointer, right? It's a system, this is pointer. So this form is the result of an ideal measurement, which has 3 fundamental properties that I'm about to write down. And importantly, it can be quantum correlated or it can be classical correlated. That's my issue. So what are the properties of an interaction? Oh, I use interaction and measurement interchangeably. I'm talking about this arrow that goes from the left to the right. What are the properties of such an interaction or measurement that result in this state, which are going to be the ideal post-measurement state? So what is it that we want when we perform a measurement? So 3 fundamental properties. First one is that the measurement from the right first is that it's unbiased. What does this mean? By unbiased, we mean that the measurement statistics are reproduced. What does that mean? That means, well, if I have a system which is 3/4 of the time in the state 0 and 1/4 of the time in the state 1, then my pointer better well also reflect those statistics when I look at it. So what this means in practice is that the trace of density on the system trace II Right, so this means that on the left-hand side, we have the probability of the pointer in outcome I. This is the pointer probability outcome I, after the interaction, after the measurement instead, after the measurement is the same as the probability of the system. Probability of the system in state I before the measurement. Okay. This is a linear constraint now that will constrain this interaction, this arrow.
The left-hand side needn't be probability. The left-hand side, the first one doesn't seem like a probability. I can put the system size as large and that part blows up, right? Like identity system, when
I'm just tracing out the system. That's what I'm. So if I just look at the pointer, which is what I'm looking at when I couple my measuring device to a system, I'm not looking at the system. I'm looking at the pointer to tell me something, right?
Yeah, but I'm not sure if the tensor product identity exists there. Like that would just when we trace it out, it would just be the dimension of the system, which would come out, right?
No, it would just remove the. It's like throwing away the system and just looking at the pointer and asking what the probability is.
Yeah, that's the second part. Okay, it's fine. Maybe we can discuss it later. Yeah.
Okay.
Sorry, Yelena, just a question. What about coherent states between the system and the pointer? Are these allowed?
Yeah. So you can have these off-diagonal terms here.
They're allowed.
Yeah. So sorry, there are things here off diagonal. There is stuff here, but in the end, we're going to find out that they don't matter because to be perfect, to be an ideal measurement, you only need to be classically correlated, and therefore we don't care about the coherences in the end. So,
but surely an ideal measurement should give you some information about the coherences of the system. Because
wait,
there's
well,
off-diagonal elements.
this is in the basis that you are measuring in. So you have to fix the basis, and in the basis of that.
So you talk about ideal measurements on a fixed basis.
Exactly. You always measure an observable, right? And then as soon as you pick an observable, you fix a basis, and in the basis of that observable, you don't care about the coherences. Exactly. The second property that we would like of an ideal measurement then is that it's faithful. Faithful means that we have perfect correlation. in practice, I am going to define a function. I'm going to call it C for correlation. This is a function that I'm going to write down. It's not a measure because it's not zero on pure states. Because in the trivial example, in this one, the state 0, 0, this is perfectly correlated. It's classical. So we want our function C to also reflect this fact. So we define this function following way. Trace. Pi I is always the pointer of the post measurement state. And to be perfect, you have to get 1. This 1 means I never make a mistake in my inference of the underlying state of the system. So clearly, in this state, it's perfectly correlated. My projector is 0, 0, tends to 0, 0, I get 1. But this is also perfectly correlated because I have 1/2 plus a half. I never make a mistake about my inference of the underlying state of the system. So, in practice, then, let's start here. This is a 1-to-1 correspondence between the pointer outcome and the post-measurement states and the post-measurement system state, post-measurement system state. So there's no ambiguity. So when I see the outcome 0, I know for sure that the system must have been in state 0. So it's also the average probability of correctly inferring the state over many rounds of the experiment. And importantly, this function is equal to 1. If you have a measurement that's unbiased, so imagine now there is some interaction taking you from the initially uncoupled system and pointer to the correlated system and pointer. And this interaction is unbiased, so you impose that it conserves the probabilities, it reproduces the statistics. Then this interaction is faithful, is equal to 1, if and only if the post-measurement state of the system is of this form. It has to be diagonal. So if I have an interaction that's unbiased, it's faithful if and only if we have something of this form. Okay, and the last property then is the property of being non-invasive. Non-invasive is, colloquially speaking, preserve the diagonal. So as was correctly mentioned, this paradigm is basis dependent, depending on which observable you choose to measure, right? So mathematically, that I want let's probability of getting the state I of the system, let's do this around, before and after the interaction are the same. Right? So the system is not disturbed along the diagonal. In the basis that you're measuring. So that means we can keep repeating the measures, right? So if I find the system in the state I can do the measurement interaction again, couple it again, and again find it in the state I. Okay.
Does each pointer row, does that belong to PI? I mean, does it belong in the support of PI? If I apply PI to the pointer state with indices I,
Yes. Pi
does that preserve it? Yeah.
Yes. If you apply this to
To the pointer with indice I,
yes.
does that preserve it?
Yes. Yes. Exactly. So.
So if I try to project it with PJ, that will
Exactly.
give
So
zero.
you're saying exactly the condition I forgot to write down is that these are orthogonal. Yes, thank you.
And we'll have to try and project that onto the pointer state with
Rho J.
what happens?
This is also orthogonal.
Yeah, okay.
Yeah. So the subspaces are orthogonal. Thank you.
Yeah, but doesn't the faithful property?
We will get to the relations right now between them. So
Does that hold anyway? Though?
no, sorry. Never.
Even for that state that you've written down there.
This faithful state holds for these. We're going to get to an example very shortly. This is faithful, correlation 1. This is faithful, correlation 1, a half and a half. But the point is, does this interaction exist? And what we'll find is there is no pointer state that exists. So let me get to that. So, okay, yeah. So that's a good time to have an example then. So example 2. Let's just do qubits because they're easy. And let's have the system be some diagonal states. It can have off diagonal terms, but I am also lazy. So this. And the pointer state I'm going to take as the eponymous pure state, the ground state. And as my interaction, I'm going to take a C naught. Right? So what I have is U C naught, row system, pointer, U C naught. And what I get in the end is a state. It's all pretty trivial. What you can do is you can check that this interaction, U C naught, and this final state, rho S prime, satisfy all these properties. And we say that a measurement is ideal when all 3 properties are satisfied. So you can check that this measurement, U C naught, is unbiased, it's faithful, and it's non-invasive, which is great. So this is something that satisfies all the properties. And in fact, you can generalize this. Perhaps I'll use a different color. If I take this pointer state to be pure, like I just did, you can generalize this interaction to a generalized U C naught, right here, generalized, where then you can have any system of any dimension, anything you like, whatever, and you will still satisfy all of these properties. So, okay, how much time do I have?
15 minutes almost. Wait, I said this before, no?
You said this like 15 minutes ago, yeah.
When is the coffee break? No, you have like 10 minutes.
10, okay. Okay, so I'll do the theorem first and then the relation. So what is my problem with this construction then? If it's so easy to do an ideal measurement that satisfies all these properties I claim to be ideal, well, why don't I come along with my pure state pointer? Maybe I can make it really big, maybe it doesn't matter. I just do this interaction all the time. Well, this is exactly the argument that we had at the beginning of the lecture, is that these things don't exist. You don't have pure states, you don't have access to pure states. You have to, call a system and approximate a pure state in some way. So let me show you the theorem, and then I'll give you some intuition as to why it should hold. Good to hear. So Theorem, so the theorem is faithful measurements. So we're going to keep these properties here. Faithful measurements, which is perfect correlation. Well, okay, so let's fix this to begin with. A measurement is ideal if all three properties are satisfied. If at least one of them fails to hold, we say that the measurement is no longer ideal. So faithful measurements, so those interactions which satisfy number 2, measurements are possible. And only if let's put it like this, the rank rho p of the pointer system before the interaction is not full. So this is a more general way of saying not pure. So the theorem or the argument here somehow is that faithful measurement, perfect correlation, never making a mistake about which measurement outcome you got, is only possible if you have a pointer state that is not full rank. So this means pure, because if I have something that's not full rank, it means I have to prepare pure states on some subsystem of the pointer somehow. Right? So I don't know if we'll get to it, but in fact, this rank is bounded. So here we get to a conundrum. I don't know if they call that in this, maybe it's a conundrum. All the marginals, and by that I mean all the subsystems of a thermal state are full rank. Here perhaps I've skipped a trick. So what I've argued is that you can't use a non-full rank pointer. So the conundrum is that all the marginals of a thermal state are full rank. So this is again goes back to the third law of thermodynamics. And the resolution to this, because what we're going to assume here is that since we don't have access to these pure states, is that this rho, we're going to take it to be a thermal state in the pointer state. Why is this a reasonable thing to assume? Well, when you go into the lab, things are typically thermalized to the temperature of the lab. You have some measuring equipment. So what we're going to do in the end is take the pointer to be some thermal state, whose marginals are all full rank. And to resolve this sort of measurement paradox between the postulates of quantum mechanics and thermodynamics, we're going to use refrigeration. Well, let's put a large enough rho pointer to refrigerate some, let's put not all, some marginals, doesn't matter, and approximate a pure state. Why do we want to approximate a pure state? Well, we saw in this example, if I have a pointer that's in a pure state, I have an ideal measurement. I can recover faithful correlations. But the consequence of all of this, talking. The consequence is that obtaining reliable information, reliable knowledge, let's say, about a system. Well, firstly, we'll see that it requires macroscopic amounts of work. And we'll tie it in with what Ralph was talking about in terms of those energy, time, and complexity constraints, that perfect knowledge is infinitely expensive. So practically, what we're going to do then is for some rho p, it will take to be thermal initially. What we can imagine doing is refrigerating this rho p. We don't have to refrigerate all of it, maybe some of it to cool that down, because as soon as I get colder, I can get a better measurement. Will we get to the proof? Do I have time to sketch a proof?
You have 5 minutes.
5 minutes, yeah, that's time. Yes. So why does this theorem hold? I'm going to keep this post in measurement state on the board because it will be useful. Imagine we have an interaction. So this is a sketch. Or maybe just the proof if you're convinced enough. So for an ideal measurement, with perfect correlation, so C, I call it till I don't remember C, no, we just C is 1. The maximum rank of the post measurement state must be bounded. So in other words, let's imagine, and I'm taking unitaries as my measurement interactions because later on in the lecture I want to talk about energy, and if I talk about general CP-TP maps, I have a problem in that I can embezzle energy, and in the end you can always find a unitary in a higher dimensional space to describe your dynamics. So, okay, the maximum rank of this thing is really the rank of this time, the dimension of this times the dimension of this one. So very cool, right? But in fact, this must be bounded by.
Can you raise the board a bit?
Sorry?
Can you raise the board a little bit?
Raise it.
Yeah. Thanks. Yeah. That's
The maximum rank must be bounded by dp in order that we get perfect correlation. What is the intuition for this? Well, okay, let's take. Let's take the post-interaction state, which I claim is the ideal form. Yeah. Let's imagine we have some three-level pointer system, right? So maybe we have 1/3, 1, 0, 0, 1/3, 0, 1, 0, and 1/3, 0, 0, 1. This is the subspace 0 of the system. Here is 1 of the system, and here is the subspace 2 of the system. Good. So also I have pointer subspaces, pi0, pi1, pi2. I haven't specified the dimension of these, so this could be many things grouped together, right? Here I have again pi0, pi1, pi2 subspaces in these columns, right? So we can kind of see by looking at this post-interaction state that if I have something that is full rank, I start making mistakes about my inference. So here, for example, I have, I see, this is the state 1, 1, tensor pi1 of the pointer. And if I see 1 of the pointer, I know for sure that the system is in state 1. If I had some kind of element here, A, this would correspond to seeing state 1 of the pointer, state 2 of the pointer. But in fact, the underlying system state is in the state 1, right? So the point is that you have to have something that is not full rank in order to eliminate the mistakes you make about your inference. In the special case, in the case that the system and the pointer dimension are the same, then the rank must be 1. Which we saw in the example I erased, right? Or here, you can see it here. So when here we have the pointer and the system have the same dimension, here I have just rank 1 things, right? So practically, if I can have a pointer that's much bigger, but if the pointer is full, so if the pointer is not full rank, that means I practically have to produce pure states on some subsystem of the pointer, which is also cheating. So that is the only way then to get the ideal post-measurement state and to satisfy these properties. And since faithful measurements, since we cannot have, since the rank of rho p is typically full because we use something that is a thermal state, for example, then we can never have a faithful measurement, right? We cannot, if we don't have access to pure states, we cannot have faithful measurements. I think that there I'm going to stop.
Very good. Thanks, Yelena. Okay, half an hour. There's coffee now.
I kept staring at the fine print.
1 hour, yes.
Okay. We will now continue Yelena's lecture, and for those who just arrived, like Renato, and just going to be about home, what we did so far, what Yelena did so far, was to define what physical measurements are, or we have a physical pointer, and then you say for them to be perfect, then they need to be like, it's obvious, so if you repeat them, you get the same outcome. If you point at you measure the pointer, then they are perfectly correlated with the system, even if some microscopic degrees of freedom of the pointer are not like this. And then she also said that to have a perfect measurements that satisfy these properties, you need to have pure states. And of course, we don't have pure states because we can't use the ground state. So now I'll let Yelena continue.
Just a quick question. What would be defined for a single basis, or do you assume that they should hold for any basis?
I'll get to that in 1 second. Okay. So, okay, so we have this theorem that faithful measurements, the ones which produce perfect correlations, are possible if and only if we can produce pure states. So then the logic goes that pure states. Sorry.
Very loud.
Pure states are not possible. No, not interested. Not possible due to the third law, right? And now I'm going to repeat what Ralph already told you. They require.
Hey, Tamara, you're here. No, I think you need to go to the other side.
No, I need that. Well, I can go there in a second. Maybe I can go.
Oh, look, really? Something happened. Yeah.
Rotate with him.
Yeah.
That again. Yeah, exactly.
What Ralph said to us in the last lecture, these pure states, which in or the ground states, which in non-degenerate cases is a pure state, requires infinite time, infinite energy, or infinite complexity. And Ralph put that in quotes. I'm going to put brackets. You know, if I specify some interaction between n components of a pointer where n is enormous, this is also very difficult in principle. So, what I want to do is summarize some relations between these three properties. Write them here. And there are some exercises where you can prove relations. So, to draw them like this. Faithful, that's number 2. And non-invasive. Number 3. And unbiased. 1. Are related in the following way. So, and you'll show this in the exercise. So if I fix a particular row S, I have one particular state in mind, I can interaction. So okay, that's here. So again, we're talking about I have a system, I have a pointer, and I'm correlating it somehow, and this is what I call the measurement. So if I have a measurement that is for some fixed state of the system, both unbiased and faithful, I draw a ring around them, then automatically for free that I get it's non-invasive. If I have a measurement that is faithful and non-invasive, so these two properties are satisfied, then automatically this implies that the measurement is also unbiased, so the statistics are preserved. So for a fixed rho S. If you relax rho S to all system states, so for example, you can imagine that you have some measurement interaction that's faithful and unbiased for some particular state, but then you change the states and you find that you don't, it's not, and it's automatically non-invasive. But if you change the state, it's not automatically non-invasive. That's no good. So now we're going to relax this to all rho S, which is what we want, because that in a measurement interaction, we don't know what's coming. That's where we're measuring it. If you relax this to for all rho S, you recover the final relation. So a measurement interaction that is unbiased and non-invasive for any, you can also say this, for any system state will automatically also be faithful. Okay. Now, since we cannot prepare pure states, the faithful property is never going to hold because we need a pure state in order to get this property. So the next question is, if the faithful property doesn't hold, ideal measurement is not possible, how closely can we approximate an ideal measurement? So that's what we'll do. And after we approximate the ideal measurement, we'll also compute how much energy it costs to do that. So we're going to make some assumptions. So faithful, the of close interaction states equals 1, not possible. Rho P must be full rank. The third law. And here we're going to take the initial state of the pointer, this rho P, to be a thermal state. Something in your lab that's at the same temperature as your environment. If it wasn't in a thermal state, then any deviation from the thermal state would require some work input, which you would also have to compute. So we're going to put it in a thermal state because that way we don't embezzle any work or miscalculate the total work. And the final thing that we're going to demand is some, I guess, minimal requirements of any measurement is that it is unbiased. So the statistics are preserved. Because what's the point in having a measurement that doesn't give you even the correct statistics you have of the pointer? I've erased it. So this also means that if the measurement is unbiased, it also means that for sufficient repetitions of my experiments, I get a mean value for the observable that correctly reflects the underlying statistics of the system as well. So that's the least we demand of a measurement. So what it means then is that in practice, this picture here, this S, this rho P, sorry, take as a thermal state. And the last thing I'm going to do assume that the measurement interaction is unitary. If it's not unitary, I have to bring in ancillas. And if I bring in ancillas, I either have to do a bigger unitary or account for the work that I do there. So by making this interaction unitary, I can clearly keep track of all the work lost in the end. Okay. So how are we going to model the measurement process now? So what I'm going to do is, I said before that the unitary orbit of all marginals of a thermal state are full rank. But what we can do is we can use cooling to approximate a thermal state. So in practice, we're going to have the following diagram for our measurements. So I have some system S, and I'm going to have a pointer, and I'm going to move to a picture where this pointer is going to be composed of n qubits. So let's draw it like this. In fact, we'll do more. So here is my system that I want to measure. And I have some pointer that I've split conceptually in half. So rho S, rho P, I take to be as you wish. I take the pointer to be some number of copies of the thermal state. The thermal state of the qubit is HP. Well, I take the energy gap to be EP. Z. And what I did, I had a big pointer composed of n qubits, and then what I did is conceptually split it into two parts. A part that I call, or label the pointer, and a part that I call the fridge. So what I'm going to do now is I'm going to use the fridge, and in particular, I'm thinking of a particular paradigm called the 1 qubit fridge. Let's call this U cool and U core for correlation. So what I do is in the beginning, I take my pointer, which is composed of n qubits, and I use something called the 1 qubit fridge, or you can use any refrigeration protocol that you like. In fact, I'm thinking of a particular reference that I have in mind by find the reference. Ralph, you're in this paper, no? So here, this is the 1 qubit fridge, and what this means, what the 1 qubit fridge does, or its special, is that 1 qubit in the fridge calls 1 qubit of the pointer. So here B1 is less than bigger than PRE. And the good thing about this fridge is that it's autonomous. So this unitary is really energy preserving. It commutes with the Hamiltonian of the pointer. And so we have a very, we can calculate the energy cost of implementing this unitary. So this is right here, conceptual split. Split. Or you can use any other refrigeration protocols that you like. After that, you have some pointer qubits that are a bit colder, and which are colder close to the ground state, so they make for better measurements. And then what we do is implement a correlating unitary. So in total, the process is something like this. I have some system, tensor tau beta n over 2, tensor tau beta n over 2, and I apply a unitary, the cooling unitary, so nothing on the system. Cool. Nothing on the system. And after that, I apply the correlating unitary. So I throw away the fridge. So then I trace out the fridge after I've done this. I don't need these things anymore. And I'm left with the thing that I call my pointer and my system. And I apply correlating. And I get this, whatever the post-interaction status that I get. Okay, so of course, when we use the fridge, we have to invest some energy into that. And when we correlate, we also have to invest some energy. And the point is that how much energy do I need to invest to cool something? How much energy do I need to invest in correlating something? And then how close can I get to do it to a perfect measurement? Right, so let me write down the formula, or any, well, I'll write down a specific formula, but it's not very important. So using your favorite cooling protocol, you call your system, also your pointer, to some lower temperature, and you have to pay for that. So total energy I require for making a measurement is obviously the sum of the cooling part plus the energy I spend correlating. So I'll quickly write down this formula of Fabian Kibasital, maybe Ralph if he's on it or not, who knows. This thing is N this one. So what are these EF and EP? So in their protocol, in order to cool something, and this achieves the cooling from temperature beta to temperature beta EF over EP. So using that protocol, the final temperature you achieve is this. So you want beta to be smaller because it's inverse temperature, remember? So 1 over T. So beta to be bigger. And clearly you can see that this formula diverges. It diverges with EF and with EP. So what you want is that the fridge, because you want this to be bigger, so you want the fridge gap to be bigger than the gap of the pointer, right? Or the conceptual split. And okay, if you want to approach the ground state, then this formula explodes. So here is where you incur diverging costs. part. The correlating part is completely finite, this part here. One way to see this is imagine that you have, imagine you have,
Keep talking, sorry.
sorry, imagine that you have n qubits all in the forbidden pure state. Then the correlating part is trivially half EP, because I told you that if I have a pure state, I can do a perfect measurement. So I don't need to use n qubits. I just need one of them. And it's enough for me to flip that one qubit in order to correlate it. That's just some intuition. But right, in general, this is always finite, and this is what you have to pay for. So now we have two questions. They are the following. So we're trying to approximate ideal measurements. So the first question is, which unbiased measurements produce the best correlations? The second one is,
Whether the energies you wrote there are the expectation values of the energies.
yeah, sorry. So delta E is the trace of E after minus, this is the energy operator, right? Or, okay, let me write the Hamiltonian. This is HP HS plus HP plus minus HS plus HP. This is final and this is initial states, right? Right, yeah, so you just can, so after you do the first unitary, you can compute this, and then you do the second one and compute again from your respective initial and final states. So the question is, okay, given that we don't have faithful measurements, which unbiased measurements, the ones which preserve statistics, give you the best correlations, because that's what we're into, and what is the smallest energetic cost of such a measurement? And maybe at this point, an aside is in order, because here we're talking really like about the fundamental foundational cost of doing a measurement. Like if you think about a hard drive in your computer that's correlating some spins, thinking of a classical hard drive, correlating some spins with some information, and then you see it right on your screen. There is, hey.
Yelena, when you say best correlations, you mean the most faithful you can
Yeah,
get?
exactly.
Okay.
As close to one as possible. So C max rho SP. Yeah, so these are kind of very fundamental costs of doing a measurement, and really, I'm afraid to say they don't have a lot to do with real life, although we're interested in foundation physics too. Because like when you're looking at your computer screen, there are, you know, or even if you're looking at a computer, imagine you have a computer in a lab and it's displaying the number or outcome of some measurements, there's billions of photons coming at you, right, all the time. So in some sense, in order for you to make that measurement, you have to maybe add other stuff like the energy of the, I don't know, the screen or something that you need to view these things on and so on. So the energy of cooling you invest, then you must correlate, and then, well, the lab is on 24 hours a day, 7 days a week with kilowatts of power. And the reason that you can see it is because your screen is on. So we're interested really in the fundamental lower bound. In reality, it's, you know, what is the magnitude bigger? Put that in brackets. Right. And this is somehow also, if you want to think about sort of real examples, I have a few. You have avalanche photon detectors in nanowires, and examples of measurements, non-ideal measurements, and things like CCDs and ion traps. In CCDs, you have dark counts a lot of the time, and things like this. When you're doing an optics experiment, for example, you actually don't have even an unbiased, the unbiased property holding, right? Because unbiased means that, imagine you have a photon detector and there's a 50-50 chance of it clicking when a photon comes, right? Photon comes, photon doesn't come. But in actual facts, photon detectors have an efficiency, right? They're not efficient. Efficiency is less than 1. So you don't have a 50-50 chance of the detector clicking, which means that automatically the measurement you're making in the lab is biased, right? So even in tabletop optics experiments, you don't have this. Okay. Well, maybe it's time. Yeah, maybe before I move on, we should do some quantum confessions. Like Philippe maybe has something to say about this. So yesterday, Philippe told us about Landau erasure. Box. I'll keep this, see. This box, and there was a piston attached to it on this side, and there was a particle inside the box. It was floating around, and then the piston was moved into the middle, so the particle was then localized into the state 0, right? So before, the state was, I guess, maximally mixed. And then we moved the piston to reset this thing, and the claim was that the cost is kT log 2. And we ended up in this rather nice pure state. So can anyone intuit maybe what happened here? Like, did we actually get a pure state? Or did we embezzle something along the way? I will point you to these two things. How do you have to move the piston in order to erase it?
Slowly.
Infinitely slowly, exactly. So Philippe mentioned that in all of his, in all of the work, so he was already working in the limits, in one, right, complexity time probably in this case, and that in all of these results you can add epsilons everywhere, right? So and this it goes to 0 infinite, your epsilon to 0. Yeah. In this limit, this is what happens. But can you ever reach this limit, right? Is it physical to assume it? And what's happened in previous works and in some papers is that some people have assumed that the Landau erasure represents the cost of resetting. So they say, this is the cost of resetting qubits or bits. You know, the information is physical. But this is a lower bound, right? It's definitely bigger or equal to this, right? And just because you have this formalism that tells you this is the lower bound, no one's told you if it's ever achievable physically, right? So the point is that, oh, no. it's definitely bigger than this, but this is a fundamental lower bound. Okay. Where was I? Does anyone else have any confessions to make?
What happens if the thermal state isn't exact, but also just an approximation?
So if the thermal state is an approximation, but it's still full rank, that means you have to have put in some work to move it out of this equilibrium states, right?
Depending if we assume that it's really in a thermal state. Like for example, in many-body physics, with like eigenstate thermalization hypothesis, it can be in a non-thermal state. It just looks thermal under some.
If it's full rank, this is all fine.
Okay.
Full rank is great. If it has some pure state subspaces, then it's not allowed. But it doesn't matter. I'm just saying full pure thermal states because I can write them down, right? And they're easy for us to write down. But you're right. It doesn't have to be thermal. It can be something close. All of these corrections, they creep in. Okay, I've got 15 minutes left. So I'm going to tell you. We'll try and answer heuristically these questions. Which unbiased measurements produce the best correlation? And what is the smallest energetic cost of such a measurement? So the cooling part is the part that diverges. And now we're interested in the correlating part, the part that costs us a finite amount of energy. Yeah. Well, you know, when you call a thermal state with the ground state of the Hamiltonian for your system. Mm-hmm.
I don't know, so sometimes like after the measurement to describe the system of
Yes.
I don't know if it's possible in that case.
You can, sure, you can write any, I mean, yes. I guess you're talking about a specific case of a state, a post-interaction state. It's, I think this all follows. It's. So, right, let's attempt in the last 15 minutes to answer these two questions. So, this is my paradigm then. I used N12 here as a mistake because for the rest of the time I'm going to use N. And I'm writing the same thing that I've written over and over again. This is a pointer, it's N qubits, and the system is also a qubit. So what measurements produce the best correlations? So the constraint I have, constraint 1, is that this unitary has to be unbiased. Okay, so in the beginning then, this rho S L N pointer is a block diagonal state, right? This is the 0 subspace of the system. This is the 1, or the excited subspace of the system. And let's call this tau beta so I don't have to write tensor n. 1, rho 1, 0, rho 1, 1. So this tau beta is clearly it's thermal, so it's a diagonal state, right? There's only this thing here. So the initial state is block diagonal. And now I have a constraint that this unitary needs to be unbiased. So what does this impose on the post-interaction state? This means that the post-interaction state, and this is with respect to the basis. So with respect to the basis, so all of this is dependent on the basis that you're measuring. So I of the system, and let's write those microstates that we had before in pointer I J M. So without loss of generality, the constraint imposed by the unbiasedness condition is a linear constraint, following structure. You have some here, matrix A00, a matrix A, let's call this 0, 1, A10, and A11. Here is the projector subspace of the pointer, pi0 and pi1. And here is again 0 of the system and the excited subspace. So here we also have things, but we don't care about them because none of the properties of a fundamental measurement actually care about coherences or off-diagonalities. We're just interested in how this block structure looks. And it turns out that to be unbiased, and you'll show this in an exercise, that the sum of this yeah. So unbiasedness will imply some linear constraint, which will imply something about the nature of those blocks. And in particular, what it will imply is that AJI is OII A tilde JI. What does this mean pictorially? Perhaps it's a bit difficult to decipher. In practice, this means that this matrix becomes of the following form. So here is row 0, 0 tilde. Here we have row 1, row 0, 0, row 1, 1. So row 0, 0 and row 1, 1 are elements of the diagonal elements of the initial system matrix, which means that these block matrices, these A tildes, necessarily are composed of the thermal populations, right? The populations appearing in the thermal state. And importantly, we have two copies of them, right? Because row S is a qubit, and when I take the tensor product, I will have two copies of the thermal state in this matrix. So that is enough for a measurement to be unbiased. A measurement to be maximally correlated, we have another constraint. Notice that I haven't told you how to construct this U. Actually, I've just told you how it should transform the elements. This is another problem. Constraint 2, what we want is maximally correlating, which is what maximally Leia mentioned a few moments ago. We want to find biggest C, which corresponds to the trace of these subspaces. Okay, so since necessarily the A tilde matrices are composed of components coming out of a thermal state, what does it make sense to do? It makes sense to sum the largest populations in the thermal state into these subspaces. Because the more correlation I can get into these subspaces, the more I'm like winning in trying to maximize my C function. So let me write here then states. And diagonal of the following populations, and I'm going to order them in decreasing order. EP, depending on how many qubits I have, this thing will be by until I get to e to the minus n beta EP. So this is this matrix, and clearly I have two copies of it, right? Because I have a qubit. So clearly, if I take the first half of the populations and then I dump them into these subspaces, then I'm doing, the best I can in order to correlate this measurement. And this is exactly what I do. So these matrices, A00 and A11, they are some permutation of the largest weights of the thermal state. The question is, which permutation are they? Because what we haven't done is told you how you construct this basis. Because this pi0 and pi1 are made up of some energy states in the basis of the pointer Hamiltonian. So in order to really minimize the energy, what I need to do is specify which states make up pi0 and which states make up pi1. And very intuitively, I put the heaviest weights next to the smallest energies. So I put these next to very low energies, and I put the rest of them in the uncorrelated subspace with the opposite energies. How much time do I have? 5 minutes. Okay. That was the intuitive picture. The proof of that the proof of that is a little trickier. So what you have to do is show that, okay, so show how to construct pi0, pi1 of the pointer. And actually the proof technique relies on majorization, which Nelly told you about earlier today. So majorization is like a tool that you can use all the time. As soon as you have a vector of probabilities, or any vector, that has a constant sum, you can normalize it, pretend it's a probability distribution, and then compare it to other normalized vectors. And this is super useful because then you can prove the superiority of one vector over another, and then show that you find an optimal one instead. So in the end, what happens is you show that there's, abstractly speaking, some vector that majorizes all other possible vectors in the set, and this one that majorizes all others is the optimal solution. And this solution corresponds to these projectors, the specification, if you like, of the basis. I'll write it, it's not terribly beautiful. So this pi1 is introducing notation that I have. And then this pi1 is 0 to 1 here. This 0 and 1 corresponds to the fact that the system is a qubit, and say using this superscript index to say which half of the ordered probability vectors to use. So K0 corresponds to the largest probabilities or the largest populations of the thermal states, and K1 to the others. In general then, I'll finish with a general picture of how to do this and comment on why that in practice is also tricky. So to summarize then, pure states aren't for free because we have to, we're subject to the third law of thermodynamics, and the best we can do is call something as close to a pure state as we can, because the closer to a pure state we are, the better measurement results we're going to get, in the sense that we don't make a mistake with our pointer. The thought of correlating your system of pointer is always finite, and there exists an explicit protocol that tells you how to do this. So This protocol I've described in terms of qubits, that it's any system and system Hamiltonian and any thermal state of the pointer, not necessarily n qubits. And we assume that we don't know anything about the system, so we'll assume it's in the maximally mixed state. Otherwise, if we knew something, we wouldn't probably need to measure it. We assign the largest dp over ds eigenvalues of now beta to the correlated subspace. And compare the largest weights with the smallest, populations, let's say. Here the smallest energies in the non-correlated subspace, HNC. So in practice, the Hilbert space, it will decompose into something like the correlated parts. Everything is block diagonal from some arguments that one can make. And right, so the last thing you do is you pair the largest populations with the smallest energies in the non-correlated subspace, and these you dump into the correlated subspace. This would be a completely general protocol for any pointer and any system Hamiltonian. But can anybody see a problem with this already inherently? Like, to assign the largest eigenvalues, what do I have to do in order to find them? I have to find the eigenvalues of a really potentially difficult Hamiltonian, and I have to order them. How much time does that take me? It could be a lot, right? If you have a very complicated Hamiltonian, finding, what is the complexity of finding eigenvalues actually? Or ordering?
If it's a large matrix, it's probably
At scale. It's n. No. But the order.
Depends if the matrix is sparse or
Yeah.
tridiagonal.
So you have to find them first, so it will be NP.
Yeah. NP.
If it's a very large matrix, it could be long-term P club.
NP.
I'm not sure, but I guess it would.
Yeah. So even this part, in order to affect this protocol, you want to be as efficient as possible is already NP. But as we kind of argued earlier, this is really representing a fundamental lower bound on how well you can do. In practice in the lab, I mean, there are billions of photons coming out of equipment all the time. So the actual cost of a measurement is huge. And we don't care too much about what it is in terms of running computation in our computers. And yeah, with that, I'll stop. Thank you.
For the lecture. So before you go away for the poster session, if you're presenting a poster today, somewhere public in the hotel, so you can stay in this room, in the other room, or outside, or in the sofas or so, and just write on Discord where you are so people can find you if they want to see your poster. Also but if someone comes to you, and there's also someone online who wants to see, just be on the voice channel and can share screen and video so people can see from outside. Yes, you can see the list of posters, it's on the website. And then you can go to the voice channel with this person. Yeah? Okay, enjoy. The poster session starts in 15 minutes.